Hello students, this is Shailaja Vibhute. Let us continue alternating current chapter. Today let us learn about capacitive circuit. It is a circuit in which an AC source is connected across capacitor only. So when capacitor is connected to AC source, how current and voltage are related? This we can show with the help of a small derivation. So let us see the derivation. Derive an expression for the current in an AC circuit with a capacitor. Draw the phasor diagram and mention the phase relation between current and voltage. Or it can be asked like this: show that the current leads the voltage by pi by 2 or 90 degree in an AC circuit containing a capacitor. Let us see how to get this relation. First you have to draw the circuit diagram. So in the circuit diagram you can observe a capacitor of capacitance C is connected across AC source. So C is capacitor connected across AC source. The alternating potential difference across the capacitor is given by V is equal to V naught sin omega t. Let us name it as equation 1, where V naught is peak value of voltage and omega is angular frequency. Let Q be the charge on the capacitor at any time t. Then the instantaneous value of V in terms of capacitance is V is equal to Q by C. Let us name it as equation 2. So substitute this in equation 1 or compare equation 1 and 2. We get Q by C is equal to V naught sin omega t. Q is equal to, shift C to that side, you will get C V naught sin omega t. Let us name it as equation 3. As we know, this one, instantaneous current I is equal to what? dq divided by dt. So substituting the value of Q from equation 3, we get I is equal to d by dt of Q value is C V naught sin omega t. Means now you have to differentiate this C V naught sin omega t. So C V naught is constant, you cannot differentiate it. So write it first, C V naught. Then differentiation of sin omega t we have to take. Differentiation of sin omega t is cos omega t into omega. So you will get I is equal to C V naught omega into cos omega t. This cos omega t can be written as sin omega t plus pi by 2. So here this is pi by 2. Okay. Then so it can be written as I is equal to I naught sin omega t plus pi by 2. Let us name it as equation 4. Here I naught is C V naught omega and it is peak value of current. Now from equation 1 and 4, when we compare equation 1 and equation 4, so what is equation 1? V is equal to V naught sin omega t, and equation 4 is I is equal to I naught sin omega t plus pi by 2. So it is observed that current leads the voltage by pi by 2 or 90 degree, and it is shown in the phasor diagram. Okay. Then based on this, let us define one important word, that is capacitive reactance. So capacitive reactance is represented by the letter Xc. So Xc is equal to 1 divided by omega c, or since omega is equal to 2 pi f, you can write it as 1 divided by 2 pi f c. It is the amount of opposition offered by the capacitor to the alternating current flowing through it. This SI unit of inductive reactance as well as capacitive reactance is same, that is ohm. So we can distinguish between inductive and capacitive reactance. Before that one, in the first diagram, means after drawing the circuit diagram, here this is phasor diagram and this is graphical representation of current and voltage in an AC circuit with capacitor. Okay, from the figure it is observed that current leads the voltage by pi by 2. You can see two colored waves here. One is for red color, another one blue color. This red color wave is for voltage and this blue color wave is for current. You can just observe the graph here. You can understand current leads the voltage by pi by 2. So current is drawn from this point. Okay. Then this is phasor diagram. Okay, fine. Now let us see the difference between inductive reactance and capacitive reactance. Inductive reactance is the amount of opposition offered by the inductor for the flow of alternating current. It increases with increase of inductance of the inductor, and it increases with increase of frequency. So expression for this inductive reactance is XL. XL is equal to what? Omega L. That's why XL is directly proportional to L. That's why it increases with increase of inductance of the inductor. And since omega is equal to 2 pi F, so F and XL, when you compare, both are directly proportional. That's why XL increases with increase of frequency. Now let us see the points about capacitive reactance. It is the amount of opposition offered by the capacitor for the flow of alternating current. It decreases with increase of capacitance of the capacitor, and it decreases with increase of frequency. If we see the expression for XC, that is capacitive reactance, it is 1 divided by omega C. So XC is inversely proportional to capacitance. That's why if capacitance increases, capacitive reactance decreases. Both are inversely proportional. Similarly for frequency. Okay, XC is inversely proportional to frequency. That's why it decreases with increase of frequency. Now let us take one important derivation, that is for LCR series circuit. Means when inductance, capacitance and resistance are connected in series across the AC source, what is the expression for resultant voltage? Let us try to get this expression. So derive an expression for resultant voltage, impedance, current and phase angle in series LCR circuit using phasor diagram. So first we had drawn the circuit diagram where it consists of resistor, inductor and capacitor. All the three are connected in series, R, L and C, across AC source. Let us take phasor diagram. This is called phasor diagram. Okay. So in the phasor diagram, VL is the voltage across inductor. This is VL. Okay. Across this inductor, VL is the voltage and it is represented along positive y-axis. This one. VC is voltage across the capacitor. This is capacitor. Across this one, VC is the voltage and it is represented along negative y-axis. VR is voltage across resistor. This is resistor. Across that one, voltage is VR. It is represented along x-axis. Okay. So this is VR. Then if you observe the phasor diagram, VL and VC, both are acting in opposite direction. So if we take XL is greater than XC, then definitely VL is greater than VC. So this VL minus VC is resultant of VL and VC. Okay, it is represented along positive y-axis. Then V is the resultant voltage of all these. This is resultant voltage. Resultant voltage of VR it is, and VL minus VC. I is the current. I is the current which is flowing through this series LCR circuit. And here we have marked one angle that is called phi. So phi is phase angle between current and voltage. Okay, so these are the symbols whatever we have drawn in the diagram, these are explained here. Okay, then to find the magnitude of resultant voltage, impedance and current, we have to choose the right angled triangle. So which right angled triangle is taken here? This right angled triangle, this one, OCB. Okay, in this OCB you can apply Pythagoras theorem here. Okay, if you apply Pythagoras theorem, you will get OB square is equal to OC square plus BC square. Okay, CB square you can say, because vectorial notation we have taken means it will be CB square. And this CB is nothing but it is OA in the diagram, that is VL minus VC. And this OC is nothing but it is VR. Okay, and this OB is resultant, that is V. So this only we are writing. Let us see the next step. So from the right angled triangle OCB, when you apply Pythagoras theorem, you will get OB square is equal to OC square plus CB square is equal to VR square, means you are substituting values of OB, OC and CB. So it is V square is equal to VR square plus VL minus VC whole square. But we have VR is equal to I into R. That means you are applying Ohm's law here. VL is equal to I into XL and VC is equal to I into XC. So all these values you have to substitute in the above equation. You will get V square is equal to VR square is IR itself square. So it can be written as I square R square plus I square, let us take common. You will get in the bracket XL minus XC whole square. So let us take I square common. When you take I square common, you will get V square is equal to I square into bracket R square plus XL minus XC whole square. Let us take the square root both sides. You will get V is equal to I into square root of R square plus XL minus XC whole square. This only shift the term, you will get V divided by I is equal to square root of R square plus XL minus XC whole square. Actually we want expression for resultant voltage. For resultant voltage, this is the expression. V is equal to, we have written now. So this is expression for resultant voltage, that is V is equal to I into square root of R square plus XL minus XC whole square. Now we want expression for impedance. So for that you shift I to this side, you will get V by I is equal to square root of R square plus XL minus XC whole square. This V by I is nothing but it is Z, that is impedance. Okay, so this is expression for impedance. What is the expression for impedance? Z is equal to square root of R square plus XL minus XC whole square. This is expression for impedance. Then you want expression for current. So I is equal to V divided by Z you will get, where Z is impedance. Now you want to find the phase angle. To find the phase angle, again take the help of that right angle triangle OBC, but now you apply tan phi. So in that right angled triangle, tan phi is equal to CB divided by OC. CB is nothing but it is VL minus VC divided by OC is VR. Okay. This can be written as phi is equal to tan inverse of VL minus VC divided by VR. Now this phase angle is represented in terms of voltage. You can express it in terms of opposition also by substituting values of VL, VC and VR. Now let us see the definition of impedance. It is the effective opposition offered by the LCR circuit to the alternating current flowing through it. Or it can be defined as the ratio of RMS value of voltage across the series LCR circuit and the RMS value of current flowing through it. Its SI unit is ohm. So this series LCR circuit is very important. Try to practice this one and let us continue in the next.